doable. It's not that bad. It's just something, like there's got to be better than this. All right. So we look at this 2, and if we're thinking, I mentioned powers of 2 before. This is 2 to the first power. This one is 2 to the second power. This is 2 to the third. 2 to the fourth power, 2 to the power of 5. If I had 6, it would be 2 to the power of 6. So I can figure out now, based on that information, that if I had n flips of a coin, I could figure out the number of outcomes based on this relationship, again, because there is consistency between the number of flips and the power of 2. So it has to be 2 to whatever n is. All right, so if I were to say, determine the number of flips, I'm sorry, outcomes for 10 flips of a coin, you could say 2 to the 10th power, or what it is actually. But sometimes the numbers get large, so large that the calculator will either overflow or just give you something that's in like some hideous scientific notation that isn't really useful for anyone. If that's the case, then we just leave it in exponent form. So if I had something like 40 flips of a coin, it would be perfectly acceptable to leave it as 2 to the 40th power. And let me just show you in the calculator. 2 raised to the 40th. Look at that monstrosity. I mean, this E12 means times 10 to the 12th power, which means move the decimal point to the right 12 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd have 3 more zeros after this number. But those 3 zeros, those would be rounded values, which means that the calculator after E8, I'm sorry, E9, after that, it's rounding, which we may not want. We're going to lose exactness when that happens. So if you have a power that's more than 9 after your E, then I say just leave it in the exponent form. Okay? And besides, I mentioned this before, exactness is always going to be preferred. So you might have a fraction like 1511 over 2562. You'd be like, well, I'm not going to leave it like that. That's ugly. Look at the decimal equivalent. That's even uglier. Leave it as the fraction. It's going to be better off for everyone. Besides, I don't have to worry about taking off credit for rounding errors if you do that. It's a win-win for everyone. Right, so 1 roll for a die gives us 6 outcomes. 2 gives us 36. I mentioned before that 3 gave us 216. 6 to the first, 6 to the second, 6 to the third. So if I had n trials, I'd have 6 to the n outcomes. And I proved it with a base of 2 earlier. So you know a base of 6 is going to get crazier even quicker. So just leave it like this. So the general formula, the base is the number of outcomes in a single trial. And the power would then be the number of trials. Now, we'll learn later on how we handle situations where maybe you have a roll of a die and a flip of a coin in the same experiment. If that's the case, we have to do some adjustments or make some adjustments to this, but that's a different story for a different time. So I'm going to pause it here. Should I pause it or and edit? Okay, so another maybe like 20 minutes or so of new stuff, because again, this probability, the underlying theories, it's so important that I don't want to rush you into the implementation of it where it's like, all right, now that you just learned this and have completely mastered it in the short period of time that you've even seen it for the first time, let's apply it. Like, I don't think it makes sense to do that. So we'll go easy from here for the rest of this class. I'll give you some more time to work on your tech assignment, and the next class we'll really hit the ground running with this material. All right, so the addition method, or the addition rule for independent, well, this topic is called independent and mutually exclusive events, but right now we're only really talking about the mutually exclusive events. That's weird. I think I took that from the textbook, that title, and even they start off with addition rule, but it really should be the other way around. So I'll take a little switcherooski on these two because mutually exclusive comes before independence. So somebody could submit that. That's, it's a little nitpicky, but I want to give some points, so it'll make it better. So addition rule is also known as the rule of or. All right. If the word or is present in a probability question, it means you're using the addition rule. That's great news for those of you who are procedural minded. You want the steps, you're looking for a keyword or. What might not be good news is the word or may not be explicitly stated. So if it's there, you're using addition, but sometimes it's implied. So it's there, it's just not written. You just have to reason it out that what they're really talking about is an either or situation. All right? So in these two cases, because we're going to start off easy, we're looking at situations where it's explicitly stated that you're looking for something or something else. We want to have a rule, we want to have a formula that we could use because coming up with sample spaces isn't always the easiest thing. Now, for a deck of cards, if you are very familiar with a deck of cards, then a sample space idea would be perfect for you. But if the first time you've seen a deck of cards is today, or maybe it's the first time in a long, long time, then you probably don't want to go that way. So, formulas, definitely worth your time. So, generally, we would say the probability of A or B. All right, two events, A or B. In this case, event A is getting a 7. B would be getting an ace. All right. So what that's telling me to do is look at the probability of getting a 7 and the probability of getting an ace, and just add them together. All right. We knew addition had to come into play because it's called the addition rule. So that kind of makes sense. There's 4 7s in a deck. There's 4 aces in a deck. So there's a total of 8 possible cards that you would want to have out of the 52. It's kind of weird because sometimes an event happening is a good thing, sometimes an event happening is a bad thing. Like, it doesn't tie directly, but when we were doing that review problem set, we were talking about z-scores and infant mortality. That was a case where, well, we didn't want to have a high z-score because that would be a high infant mortality. That's not a good thing. Right? So, but generally, the answer to a probability question is what you would want to have in terms of successes, but sometimes we define success differently. Like if I were to say, I bought a car, the probability that the engine will explode on that car or in that car is 1 out of 20. What's the probability that if I buy 5 cars, the engine will explode all 5 times? We would define success as the engine exploding in terms of the problem, but I don't think anybody sitting in the car would define that as a successful moment, right? So it is a matter of perspective, but here what it is, what I'm looking for is, did I get what I was looking for, right? What I was looking for may not be what I actually want to have happen, but did what I was looking for happen? So I'm dealt cards. Anytime I'm given a 7 or an ace, I'm happy because that means I've succeeded. So what this is telling me is that if somebody were to deal out 52 cards in total, I would be happy 8 out of those 52 times because 8 out of those times I would have either a 7 or an ace. All right? Or does not imply choice. Right? Because if I tell a person that, like Charlie's going to come walking in, what are the chances he's wearing a red shirt or a green shirt? It kind of implies that I'm saying two separate things. What are the chances he's wearing a red one versus wearing a green one? Because he's obviously not going to wear them both at the same time. Oh, actually, no, that's not obvious. He could be wearing a shirt that's both red and green. Not the blending of the two, maybe it's like striped or something. So that's a possibility. A lot of things come into play, but it's not a neither or. Both could happen. So we have to account for all ways in which you could have a success. All right? In the form of what's known as a Venn diagram, I'll draw a little box here. The box represents the entire sample space. This is kind of a nice way of representing all possible outcomes without listing all possible outcomes. All right, so somewhere in this sample space, I'd have a set of cards that are 7s. And somewhere else, I'd have a set of cards that are aces. The 7s happen 4 times. The A's happen 4 times. Total of 8 cards out of 52, which means that there are, simple math here, 46? No, that would be 44. Other cards. 44 cards that are not 7s or aces. Right? Generally, we make the Venn diagram really to support our understanding of the answer. I don't often see how you get the answer just from the Venn diagram without having some calculations. But what sometimes they'll say is, here's a Venn diagram, whoever they are. Here's a Venn diagram. You have 44 cards that are not what you're looking for. 4 cards that are 7s, what's the probability of getting an ace? So then if you have 52 cards overall, that you're missing 4 cards, so 4 out of 52, you can kind of pull it from the diagram. Right? But really, that's not the point behind this diagram. This diagram is to show that there's no overlap. And so what we're looking at are mutually exclusive events. They're mutually excluding one another. The 7s are having a party. No A's are invited. The A's are having their own party, probably out of revenge. And no 7s are invited. Right? They're excluding each other from their groups. Right? They're very cliquey. That's the case of mutually exclusive. And also, why do we identify as mutually exclusive or not? It's an indication of how much work we have to do. Because if 2 events are mutually exclusive, you can just simply add their associated probabilities and call it a day. In the second example, we have a case that is not mutually exclusive. So again, probability of A or B, some event A, some event B, where A is getting a 7, B is getting a red card. So I could try to set it up the way I did the previous one, and to an extent I'll be somewhat right. But just looking at the Venn diagram related to this, or at least in constructing the Venn diagram, you might have cause to ask a question or two. Let me just slide this down a little. just put my reds in here. So this would be my set of reds. And there's 26 in the deck. Half the deck is red, half the deck is black. The question would probably come when you're creating this of, well, how do I draw the sevens? Because there are some sevens that are also red. So we're going to have a little bit of overlap here. So these are my sevens. Now, if I'm only focusing on, let's say, the red sevens, the overlap between the two sets, there would be a total of 2 of those. You have the 7 of diamonds and the 7 of hearts, which means I have also 2 cards that are the sevens that are not red, so the clubs and the spades. So by drawing the Venn diagram accurately, I'm able to figure out what I need, because what I have here is a total of 30, I believe. Sorry, it shouldn't be 30, because this number should be 24. All right? Because these are the reds that are not 7. I'll be a little bit more specific here. These are the 7s that are not red. All right? So in doing that, we get a total of 28 cards out of the 52 that are available. All right? But that, even I got jammed up on that. So then you ask yourself, how are we supposed to do it? You guys go. Well, that's where the formula comes in, because if the formula is going to be the more useful way to go, there must be a reason for that. All right? So if you know that there is some kind of overlap, you can just add the 2 probabilities of the individual sets as if there was no overlap, but then subtract off the overlap, the cards that are red and 7 at the same time. So the benefit of doing it this way is because we already know that there are 4 7s in a deck. We already know that there are 26 reds in a deck. And all this information, you know, these kind of questions, deck of card questions, don't really lend themselves to a test because they require you to know about the deck of cards. So this is what happens. You either get a question related to some fictitious scenario that doesn't involve a deck, or be on the lookout on the very last page of your test for this diagram. All right, so because it's not a test on your knowledge of a deck of cards. It's a test on your knowledge of probability. So at this point, you'd have to say how many red 7s are there. Looking at your sample space, you'd say that there are 2. This would be the 7 of hearts and the 7 of diamonds. Red and 7. Yeah, that's an ampersand symbol. All right, so when you do the math here, and fraction form ends up being the best way to go. I mentioned this earlier because you can get exact answers and all that stuff. But the one thing that didn't come up at that time is it's also more convenient because we have a common denominator here, which means all I have to do is combine the numerators. 4 plus 26 is 30, minus 2 is 28, and keep the denominator as is. So we get our probability that way. All right? It's a little bit more convenient. Not to say that this is the easiest thing in the world to wrap your brain around, because it's definitely not. And I'll tell you that this one concept, when people struggle with probability, it's simply because of this. Because everything else it's based in some way on your knowledge of these relationships. All right? So how do we know? Well, if there's overlap. Overlap means that whatever the event is, whatever the object is, it can embody characteristics of both scenarios. So in this case, you have 7 and red your question to yourself would be, can a card be both 7 and red at the same time? If the answer is yes, then you can't just simply add the two probabilities. You have to subtract something. And in fact, I could have used this rule for that last question. I could have said P of 7 plus P of 8 minus P of 7 and 8. And then I would have done 4 out of 52 plus 4 out of 52 minus 0 out of 52, because there are no cards that are both 7 and 8 at the same time. What? So using the same rule, I get the same answer, just I'd have a little extraneous component that I don't need. No, no, do not. That's the other benefit of using a fractional answer, is that you'll never have to reduce. This would be the final answer. There's a couple reasons for that, but I think the most important one is the idea that since the denominator always represents the number of elements in your sample space, this gives you a pretty good sense of what's going on. Because like, it would be, let's say this is a 26 out of 52 final answer. You could say half the deck is red, half the deck is black, but that doesn't really tell you the full story. Because if a person goes into a situation being like, okay, half of a deck is red, half a deck is black, and then the question is like, okay, how many cards are red? You're like 300. Like, where'd you get that from? Well, I have no idea how many cards are in a freaking deck, so I just made up a number. 600 cards in a deck. I cut it in half. 52, that denominator tells you how many are available. When you have that 26 on top, you know that there's 26 ways to succeed. All right. And also, you don't have to simplify as a student. This? 28. Here? 24, 2, and 2. Yeah, from a student standpoint, yeah, I'm just being nice. You can look at it that way. Oh, he's not making us reduce. What a nice guy. That's a byproduct of it. It's great that you don't have to reduce, but there is a reason for it. And also, you notice in this case here, these numbers, if I reduced them, they would all, I think, have the same denominator. So you could still combine them in reduced form. But sometimes, depending on the numerator, sometimes this will reduce to be, let's say, over 13, but maybe this one will only be over 26. Then you're going to have a hard time combining them. So you're actually even better off, just for the math behind it, adding and subtracting, to have it in unreduced form, because it guarantees a common denominator. So even better. You know, there's a lot of different ways to justify that. I looked at that page number like 4 times.